Hello everyone, welcome to Gamma Classroom. Today I'm going to introduce direct current circuit 1.3, scientific notation and metrical prefixes. 1.3-1 Scientific notation. In many disciplines of science and engineering, very large and very small numerical quantities must be managed. Some of these quantities are mind-boggling in their size, either extremely small or extremely large. Take, for example, the mass of a proton, one of the constituent particles of an atom's nucleus. One proton mass is equal to 0. So many zeros. The last three digits is 167 grams. This is one proton weight is equal to this number grams. Or consider the number of electrons passing by a point in a circuit every second with a steady electric current of 1 amperes. We already learned in previous video about the amp 1 amps. If you are interested, please check the previous video from Gamma Classroom. 1 amp equal to 625 with so many zeros electrons per second. It's a lot of the zeros. It can get quite confusing to have to handle so many zero digits in numbers such as like this. Even we use a calculator or compute, we still will feel confused. Take note of those two numbers and of the relative sparsity of non-zero digits in them. For the mass of the proton, all we have is a 167 preceded by 23 zeros before the decimal point. For the number of electrons per second in 1 ampere, we have 625 followed by 16 zeros. We call the span of non-zero digits from first to last, plus any zero digits not merely used for place holding, the significant digits of any number. The significant digits in a real-world measurement are typically reflective of the accuracy of that measurement. For example, if we were to say that a car weighs 3,000 pounds, we probably don't mean that the car in question weighs exactly 3,000 pounds, but that we have rounded his weight to a value more convenient to say and remember. That rounded figure of 3,000 has only one significant digit. The 3 in front, the zeros, mainly serve as placeholders. However, if we were to say that the car weighed 3,005 pounds. The fact that the weight is not rounded to the nearest 1,000 pounds tells us that the two zeros in the middle are not just placeholders, but that all four digits of the number 3005 are significant to its representative accuracy. Thus, the number 3005 is said to have four significant figures. In like manner, numbers with many zero digits are not necessarily representative of a real-world quantity all the way to the decimal point. When this is known to be the case, such a number can be written in a kind of mathematical shorthand to make it easier to deal with. This shorthand is called scientific notation. With scientific notation, a number is written by representing its significant digits as a quantity between 1 and 10, or -1 and -10 for negative numbers, and the placeholder zeros are counted for by a power of 10 multiplier. For example, 1 amp equal to 625,000 so many joules electrons per second. We can express it as 1 amp equal to 6.25 times 10 power 18 electrons by second. 10 to the 18th power means 10 power 18th means 10 multiplied by itself 18 times, like 10 times 10, this total 18 times, or a 1 followed by 18 zeros. This is 1. They have the 1, 2, 3, 4, 5, 6. 3 times 6, 18 zeros. Multiplied by 6.25. It looks like 625 followed by 16 zeros. Take 6.25 and skip the decimal point 18 places to the right. The advantages of scientific notation are obviously the number isn't as unwieldy when written on paper, and the significant digits are plain to identify. But what about very small numbers, like the mass of the proton in grams? We can still use scientific notation, except with the negative power of 10 instead of a positive one, to shift the decimal point to the left instead of to the right. A proton mass equal to 0. So many 0 and 167 grams. We can express it as proton mass equal to 1.67 times 10 power negative 24 grams, because they have the 0, 24. 10 to the minus 24th power. It means 10 power minus 24. Means the reverse 1 divided by x. This x is equal to 10 multiplied by itself 24 times. It's equal to this one, 1 divided by 10, 24 times. Or a 1 preceded by a decimal point and 23 zeros. Why is 23 zeros? Because after the decimal, they have 23 zeros plus the last digit 1. The last digit 1 is the 24th from the decimal point. This before have 23 zero and plus the last 1. It is power minus 24. Multiply it by 1.67. It looks like 167 preceded by a decimal point and 23 zeros. Just as in the case with the very large number, it is a lot easier for a human being to deal with this shorthand notation. As with the prior case, the significant digits in this quantity are clearly expressed. Because the significant digits are represented on their own away from the power of 10 multiplier, it is easy to show a level of precision even when the number looks round. Taking our 3,000 pound car example, we could express the rounded number of 3,000 in scientific notation as such. Car weight equals 3 times 10 power 3 pounds. If the car actually weighed 3,005 pounds, accurate to the nearest pound, and we wanted to be able to express that full accuracy of measurement, the scientific notation figures could be written like this: car weight equal to 3.005 times 10 power 3 pounds. However, what if the car actually did weight 3,000 pounds, exactly to the nearest pound? If we were to write its weight in normal forms, 3,000 pounds, it wouldn't necessarily be clear that this number was indeed accurate to the nearest pound and not just rounded to the nearest 1,000 pounds or to the nearest 100 pounds or to the nearest 10 pounds. Scientific notation, on the other hand, allows us to show that all 4 digits are significant with no misunderstanding. Car weight equals 3.000 times 10 power 3 pounds. Because in this significant, they have 4 digits. It means this weight is nearest the last point. The last point, because this is 10 power 3. So this weight is nearest the pound. Since there would be no point in adding extra zeros to the right of the decimal point, placeholding zeros being unnecessary with scientific notation, we know those zeros must be significant to the precision of the figure. 1.3-2 Arithmetic with scientific notation. The benefits of scientific notation do not end with ease of writing and the expression of accuracy. Such notation also lends itself well to mathematical problems of multiplication and division. Let's say we wanted to know how many electrons would flow past a point in a circuit carrying 1 amp of electric current in 25 seconds. If we know the number of electrons per second in the circuit, which we do, then all we need to do is multiply that quantity by the number of seconds. The seconds is 25 to arrive at an answer of total electrons. We know the electrons per second for 1 amp is 6.25 times 10 powers 18. This per second times 25 seconds. We can get 156.25 times 10 power 18. That means is the electrons passing by in 25 seconds. Using scientific notation, we can write the problem like this: 6.25 times 10 power 18 electrons per second times 25 seconds. If we take the 6.25 and multiply it by 25, we get 156.25. So the answer could be written as 156.25 times 10 power 18 electrons. It means in 25 seconds, there are 156.25 times 10 power 18 electrons pass through 1 point. However, if we want to hold to standard convention for scientific notation, we must represent the significant digits as a number between 1 and 10. In this case, we would say 1.5625 multiplied by some power of 10. To obtain 1.5625 from 156.25, we have to skip the decimal point 2 places to the left. To compensate for this without changing the value of the number, we have to raise our power by 2 notches, 10 to the 20th power, instead of 10 to the 18th. So we can join 1.5625 times 10 power 20 electrons. Because the scientific put the first significant number is between 1 to 10. Actually, it's 1 to 9. The maximum is 9. So this number is 1. So the decimal should put after the first significant. So the number is 1.5625 times 10, 20. Because before is 18th. Plus this 2, the decimal from this point, move to this one from the right, move to left. So it's reduced 100 times. So in the power, in this side, we have to increase 100 times. So the power number 18 change to 20. What if we wanted to see how many electrons would pass by in 3,600 seconds? It means it's 1 hour. To make our job easier, we could put the time in scientific notation as well. This number is 6.25 times 10 power 18. It means electrons pass 1 point per second. And this number 3.6 times 10 power 3. It means it's 1 hour. It means 3,600 seconds. To multiply, we must take the 2 significant sets of digits, 6.25 and 3.6, and multiply them together. This means 6.25 from this, and times 3.6 from this. So we get 22.5. And we need to make the 2 powers of 10 and multiply them together. From here is 10 power 18 times this one 10 power 3. So we write this formula: 10 power 18 times 10 power 3. Because the exponents with common base, so put the power number added. So equal to 10 power 18 plus 3 equal to the 10 power 21. So the answer is, we get 2 sets of numbers. One is from 6.25 times 3.6 equal to 22.5. The other one is 10 power 18 times 10 power 3 equal to 10 power 21. We put together is 22.5 times 10 power 21 electrons. This number means in 1 hour, 1 hour, it means 3,600 seconds. So many electrons will pass through one point. Since the standard scientific notation are required, the number before the decimal number should be between 1 to 10. Since this one is 22.5, before the decimal point is 22. So we should move the decimal point from this point to the left after 2. It means the point from this point should move to this point. Keep this number, means this number between 1 to 10. Since this changes, this number is reduced by 10. So for keep the value the same, we have to increase number in this side. This is power 20, the 10 power 21. So we have to increase by 10. So this number will change to power, the 10 power 21 plus 1 equal to power 22. So the standard scientific notation should be 2.25 times 10 power 22 electrons. To illustrate how division works with scientific notation, we could figure that last problem backwards to find out how long it would take for that many electrons to pass by at a current of 1 amp. We already calculate the electrons in 1 hour. Total is 2.25 times 10 power 22. We know the number electrons per second is 6.25 times 10 power 18. So we can get the formula is 2.25 times 10 power 22 divided by 2.5 times 10 power 18. Just as in multiplication, we can handle the significant digits and the powers of 10 in separate steps. Remember that you subtract the exponents of divided powers of 10. According to the formula, 2.25 times 10 power 22 electrons. That means it's total electrons in 1 hour. And divided by 6.25 times 10 power 18, it means is electrons per second. We can change the formula to 2.25, this number, and move this number to here, divide by 6.25, and times the power 10 power 22 is come from this one. Because this is divide, so it's divide the 10 power 18 is come from this. So we can get the number. These two numbers divided equal to 0.36, and times this one is power 10 power 22 minus 18. So we can get the number 0.36 times 10 power 4. Since the standard scientific notation requires the number before the decimal, the number should be between 1 to 10. And this number is 0. So this number is not the standard scientific notation. We have to move this decimal point from this position, move to this side after 3, like this. It should be changed to 3.6. Since this number is increased 10 times, so we have to keep the total value the same. So we have to reduce this number by 10. So this number should be changed as 10 power 4 minus 1. So we get the standard scientific notation should be equal to 3.6 times 10 power 3. This is exactly the same with 1 hour. This means 3,600 seconds, because the unit for this one is second. And the answer is 0.36 times 10 power 4, or 3.6 times 10 power 3 seconds. You can see that we arrived at the same quantity of times. It's 3,600 seconds. Now you may be wondering what the point of all this is when we have electronic calculators that can handle the math automatically. Well, back in the days of scientists and engineers using slide rule analog computers, these technicals were indispensable. The hard arithmetic dealing with the significant digits figures would be performed with the slide rule, where the powers of 10 could be figured without any help at all, being nothing more than simple addition and subtraction. 1.3-3 Metrical notation. The metrical system, besides being a collection of measurement units for all sorts of physical quantities, is structured along the concept of scientific notation. The primary difference is that the powers of 10 are represented with alphabetical prefixes instead of by literal powers of 10. The following number line shows some of the more common prefixes and their respective powers of 10. This is the metrical prefix scale table. In this point, it means 10 power 0. This point. From this point, go to left. This means 10 power 1. We call deca, right? DA. And this point is 10 power 2. We call hector, right to H. And this point, you see, is 10 power 3. We call kilo, We call kilowatt, kilometer, it means it's 1000. And this one, we call 10 power 6. We call Mach. We always call Machbit, Machbit for the internet speed. And this one, we call 10 power 9 with gigabyte. We have all the gigabyte. 10 gigabyte, 4 gigabyte. And this one is 10 power 12, called Tera, T. This is from this point, go bigger, go bigger. And from this point, we go to right side, it goes smaller. And this point to this point, this means 10 powers minus 1. We call DC, D. Same, 10 power minus 2, we call centi, this point. And this, we call 10 minus 3, meaning we have the millimeter, right? It means 10 minus 3 meters. And this one, we call micro, is 10 power minus 6, micro. And this one is called nano, is 10 powers minus 9. And this one is 10 power minus 12, called pico. Use P, because this is number M, this is mu, is N, the P. So looking at this scale, we can see that 2.5 gigabytes would mean 2.5 times 10 power 9 biters. We all call 2.5 billion biters. Likewise, 3.21 picoamps would mean 3.21 times 10 power minus 12 amperes, or 3.21 divided by trillions of an amp. Other metrical prefixes exist to symbolize powers of 10 for extremely small and extremely large multipliers. On the extremely small end of the spectrum is femto, F equal to 10 power minus 15. Ento is A is equal to 10 powers minus 18. Zipto is Z, we use Z, equal 10 power minus 21. Yocto, Y, equal to 10 minus power minus 24. You don't need to remember those because too many. You can find those symbols. Use Google online. You can find it easily. On the extremely large end of the spectrum, P is equal to 10 power 15. E equal to 10 power 18. Zeta, Z equal to 10 power 21. Iota equal to 10 power 24. We can put the two tables together. In the left side is on the extremely small end of the spectrum. On the right side is on the extremely large end of the spectrum. You see, this one is 10 power minus 15, and this one is 10 power 15. That means the same distance from this point to the midpoint, with this point to the midpoint. This is large, this is smaller. Use the capital, but this one is use the small alphabet. F, this is P, this is E, this is Z. This is Z, right? This is zipto, this is zeta. And this is Y, this is small, and this is capital. It means it's 10 power 24. And the small letter Y, it means it's 10 power minus 24. Because the major prefixes in the metrical system refer to powers of 10 that are multiplies of 3 from kilo on up and from meaning on down. It means from mid 10 power 0, go up is kilo, go down is meaning. Metrical rotation differs from regular scientific rotation in that the mantissa can be anywhere between 1 and 999, depending on which prefix is chosen. For example, if a laboratory sample weighs 0.000267 grams, scientific notation and metrical notation would express it differently. If we use scientific notation, we can express as 2.67 times 10 powers minus 4 grams. We can use the metrical notation we can call 267 micrograms, because micrograms here is 10 powers minus 6. Minus 6 plus this 2. So this means 10 power minus 4. The same figure may also be expressed as 0.267 milligrams, or called the 0.267 milligram mg. Also, it is usually more common to see the significant digits represented as a figure greater than 1. In recent years, a new style of metrical notation for electrical quantities has emerged, which seeks to avoid the use of the decimal point. Since decimal points, these points are easily misread and or lost due to poor print quality. Quantity such as 4.7K may be mistaken for 47K. The new notation replaces the decimal point with the metrical prefix character, so that 4.7K is printed instead as 4K7. Our last figure from the prior example, 0.267 m, would be expressed in the new rotation as 0m, m means minute, 267. 1.3-4 Metrical prefix conventions. To express a quantity in a different metrical prefix that what it was originally given. All we need to do is skip the decimal point to the right or to the left as needed. Notice that the metrical prefix number line in the previous section was laid out from larger to smaller, left to right. This layout was purposely chosen to make it easier to remember which direction you need to skip the decimal point for any given convention. Example problem. Express 0.000023 amperes in terms of microamperes. 0.000023 amperes has no prefix, just plain unit of amps. From units to micro on the number line is 6 places, power of 10 to the right. This is the norm 10 power 0, and this is the micro. Is 10 power minus 6 minus 6. So we need to skip the decimal point 6 place to the right. So this is the decimal point. Move 6 place 1, 2, 3, 4, 5, 6. So move this point to here, to this point. And the unit should be changed to microamp. So 0.000023 amps is equal to 23 microamp, or is 0.023 milliamp, because the milliamp is in the 3 places here. Is 10 power minus 3. So move the decimal point to the right 3 places. From here, the 1, 2, 3. So the decimal point should be here. It's 0.023 milliamp. But this one still have the point here. So this is better. Example problem. Express 304,212 watts in terms of kilowatts. This 304,212 watts has no prefix, just plain unit of watts. From the long place, from this place to kilo place on the number line is 3 places, powers of 10. This is 10 power 0. This is kilo, is 10 power 3. It's to the left. So we need to skip the decimal point 3 places to the left. So 304,212 watt. You can write to the 304 0.212 kilowatt. Because this is the kilo, K is the 3 places this point. So this decimal from here move to the left 3 places. So from here move to here. So this is called 304.212 kilowatt. Example problem. Express 50.3 megohms in tenths of milliohms. We know the 50.3 megohms. Meg is equal to 10 power 6. 50.3 megohms. We can write down to this forms 50.3 times 10 power 6, because the meg is in power 10 power 6 from this point. The long point is 10 power 6. So we can write down to this form is equal to 50.3 times 10 power 6 ohms. Since this unit is ohm, we can write down to this formula like this: 503000000. We can think about the decimal point is in the last point, last zero, after last zero. This is the decimal point. And because this unit is ohm, if we want to change the ohm to the milliohms, since the milliohms is in the right side of the long, so the number is power 10 power minus 3. So we should move the decimal point from this point. It means from this point to the right side 3 places. Is 1, 2, 3. So this point should be here. And the unit should change to milliohms. This is the unit is ohms. And this milliohms, we move the decimal from this point to this point. So we can write down to the scientific forms is 50.3 times 10 power 9, because this have 6, 1, 2, 3, 4, 5, 6, plus this 3, 7, 8, 9. So the total equal to 50.3 times 10 power 9 milliohm. The unit is milliohm. From the megohms to the milliohms, the difference is 10 power 9. This is the O that we should learn in this video. Let's review all the main points in this video. Number 1, significant digits are representative of the real-world accuracy of a number. Number 2, scientific notation is a shorthand method to represent very large and very small numbers in easily handled form. Number 3, when multiplying two numbers in scientific notation, you can multiply the two significant digit figures and arrive at a power of 10 by adding exponents. Number 4, Follow the metric prefix number line to know which direction you skip the decimal point for conversion purpose. Number 5. A number with no decimal point showing has an implicit decimal point to the immediate right of the furthest right digit, i.e., for the number 436, the decimal point is to the right of the 6. As such, 436 point. The point is the last position. Number 6. When dividing two numbers in scientific notation, you can divide the two significant digit figures and arrive at the power of 10 by subtracting the exponents. Number 7. The metrical system of notation uses alphabetic prefixes to represent certain powers of 10 instead of the lazier scientific notation. Thank you for watching. See you next time.